Hello, everyone. Welcome to another Q&A about history of science and technology. So, let's see. The first question here about the Big Bang, which I think belongs in a different Q&A. Frank is asking, what historical scientific question do you think could have been solved much earlier with computational tools? Well, there are certainly things in math that would have been greatly informed by computational tools. That's the most obvious one that comes to mind for me. There are, well, yes, there are a few other obvious ones. Given Newton's theory of gravity back in 1687, maybe it was Hooke's theory of gravity, one isn't quite sure, but the inverse square law, that in principle would have given one the information to be able to compute the motions of planets. But it took another 200 years to get that really under control. And that was for example, Newton tried to compute the motion of the moon and really ended up just getting the wrong answer because he had the correct underlying physics, but didn't have the ability to actually work out the effect of the sun, the earth, the moon, and their mutual gravity and so on. So that's a case where, in the end, with modern computing technology, it's easy to do that. You can do it in you can do that computation, at least the basic one with three bodies, using the ND-solve function of Wolfram language immediately. It's easy. To take account of Jupiter and other bodies in the solar system, it's a bit more difficult, but that's something that would be sort of immediately computationally solvable. But in Newton's time, using sort of algebraic methods and so on, and using various approximations, it was something couldn't really be done. Now, in terms of other kinds of things, there are cases in physics, for example, where just being able to do a lot of computations eventually reveals patterns that weren't clear before. That's happened, for example, in computing Feynman diagrams in quantum field theory, something I was very interested in the late 1970s, and had in fact was on this exact path of you just do lots of computations and you see the patterns of the results you get out, and then you realize there's a bigger picture of kind of how you can compute these results, and a sort of a bigger structure that is revealed by the regularities that exist in those kinds of computations. Now, then there are other things in mathematics. There's endless experimental mathematics that could have been done by people over a long period of time with better computational tools. I mean, many of the obvious greats of mathematics from Gauss onward did experiments. They kind of worked things out explicitly with particular numbers to try and work out something like the density of primes, and they would have found that a lot easier with computers. Ramanujan, for example, in 1910 or so, was himself a very good hand calculator. He would have been greatly assisted by Wolfram language and so on. People have often commented on how much further Ramanujan would have been able to get if he'd had the modern tools that we have. I do remember when Mathematica first came out in 1988, one of its reviews was rather charmingly titled, "What if Gauss had a mouse?" And it was really kind of a bit of an analysis of what could be done with Mathematica as it existed in 1988 relative to what Gauss had been able to do in the early 1800s in the things he'd done by hand. I think one of the bigger things that computation could have achieved in the distant past is a structuring, a formalization of things that really was only developed much, much later. I mean, Leibniz, for example, in the late 1600s, was thinking about kinds of structuring ideas, his characteristica universalis, his kind of universal language for representing things. These were sort of proto-computational ideas that could have been much more developed if he'd actually had the ability to do computation at the time. Um, I think uh, there are many, many other places where sort of things were limited by computation, but sometimes also things were limited by imagination that wasn't present when one wasn't used to computation. An example of that would be gene sequencing, where I don't know quite how much earlier shotgun sequencing, where you're just sort of sequencing small stretches of DNA and then figuring out with a computer how to solve the puzzle of fitting all of those together. Not quite sure how much earlier that could have been done. My guess is it could have been done somewhat earlier if that sort of computational idea had been clear, and of course, if the computers had existed to be able to do all of that matching. Let's see, a similar question here from Jason. If the tools we have now existed centuries ago, which scientist would have been most excited by them? I think many scientists who have been able to achieve a lot used every tool they could. I mean, Newton was always doing physical experiments on things. Sometimes they involved doing things to himself, so to speak, to understand things about optics by poking things in his eyes and so on. Um, Leibniz was making sort of mechanical calculators to try and understand more about how to calculate. I think he also was imagining he would be in the same kind of business that I've been in, of making actual commercial tools for doing mathematical computation. That didn't work out for him. It took him basically 30 years to get this mechanical brass calculator to work. He wrote this kind of nice documentation for it, along with kind of almost ads for, use this mechanical form of calculation and so on. I think in more recent times, certainly Turing would have been most excited by a lot of things we've been able to achieve. I mean, he sort of described sort of the beginnings of some of the kinds of symbolic computation capabilities that we built now in Wolfram language. He also described the beginning of kind of a Wolfram Alpha-like play. He was working out, just how much knowledge is there in big encyclopedias and so on. What would it take to make that computable? Leibniz, many, many years before that, for Turing, that was around 1950. For Leibniz, it was in around 1700. He was thinking about kind of what would it take to get a library assembled that could kind of make things make things as we would now call it computable. Let's see. Keeping going here. Well, Christian asks, how much of our current computational infrastructure and technology is a historical accident? It's an interesting question. Whenever we look at a QWERTY keyboard or a non-English language equivalent of that, that detailed layout is surely a historical accident. It was done at the time when typewriters were made. It was tried to be set up in part so that there are various apocryphal stories about why the keyboard layout was done the way it was done. I think a significant and probably correct story is that when you press sort of keys with your left hand and your right hand and so on, the goal was to have common sequences of letters not be such that the kind of the levers, that the metal levers that would actually hit the ribbon and so on got tangled up. That might also be an apocryphal story, and it might be that somebody just laid it out that way because that was the way they thought of laying it out the day they did it. So, there are things like that that are sort of arbitrary at that level. There's, the fact that, what was it, Control-Alt-Delete for rebooting. I think that still works on Windows machines. That was sort of an arbitrary choice at the time. The fact that sort of the sizes and shapes of things are the sizes they are, the screen sizes, the aspect ratios of screens, all those kinds of things. The detail of whether you have 50 or 60 hertz or whatever frequency for your mains, for your electrical supply, or whether it's 110 volts or 240 volts or whatever. There are many specific parameters which I think are surely historical accidents. In terms of kind of how, I think the history of technology, history of engineering in general is kind of a story of historical accidents in somewhat the same way that biological evolution presents to us now species, many of whose details are sort of historical accidents. I think there's a slightly different profile of what gets figured out by humans than what happens by sort of the kind of no humans in the loop forces of biological evolution. I wrote about this recently in connection with studying kind of the game of life cellular automaton, where there's kind of 60 years of work that's been done, on the one hand, by people explicitly constructing things, and on the other hand, by searchers, where you're just sort of blindly searching some large space of possibilities. I think, well, when it comes to other kinds of things, it's been sort of interesting to see that there are ideas in the history of computing that arose very early and took a long time to mature. Sometimes an idea gets made and unmade and made and unmade and so on. A good example of this is centralized versus decentralized computing capabilities. Back in the very distant past, it was kind of when it was kind of mechanical calculators. It was one calculator per person, a personal computer, so to speak. Then when electronic computers started to come into existence, they started to be expensive and more centralized. When mainframe computers came into existence in the late 1950s, early 1960s, things like the IBM 360 and so on, that was a very centralized story. It was a story of where there would be one big computer in its special room with special people tending it, and you would sort of feed jobs into that computer. By the time I was using mainframe computers in the mid-1970s, that was a story of, you take your deck of cards, you put it in, you submit it to physically put it somewhere where somebody will pick it up, and then when you get the results, they come back as a printout that's a folded piece of line printer paper that got, in the case that I was using it, got put. I don't know whether the people who were operating the computer were actually wearing white coats, but they might have been. It got put in a kind of a wooden pigeonhole for one to pick up when the job had been run on that computer. It was a very centralized thing. The idea of time sharing came in the early 1960s, actually, became more common. Again, it was a story of having many people use a centralized computer. In my own sort of life, I first started using a computer around 1973, and that was a large computer that only one person used at a time. It was a thing the size of a desk, programmed with paper tape, and you would feed the paper tape into the computer, and the computer would grind away on what you wanted it to do, and you would get the results, and then another person would come and do that for their program. It was sort of a single user computer, but in a centralized place, so to speak. So nobody sort of had that on their desk. Then I started, using a mainframe computer that I just described, where you get the results back kind of in the pigeonhole, so to speak. Then I started using the ARPANET in 1976, the forerunner of the internet. And there I was using centralized computers. Particularly, I was in England at the time, but particularly I was using a computer at MIT that was part of Project Mac, the multiple access computer, or it had a variety of different possible meanings for that acronym. But kind of the idea was that was a time-shared computer that people could log into from sort of anywhere in the world and do their thing. Well, or at least anybody who had access to the ARPANET, which was still quite a limited set of places. But then in personal computers started to come in. That was already by 1978. There were some personal computers. I think, when was the Apple II? That must have been around that time. I certainly wasn't using that. I was using computers that were time-shared computers that were of varying sizes. But it was, again, a sort of centralized computing story. By the time the PC came out in, when was it, 82 or so, maybe 81 perhaps, then the Mac came out in 1984, And this was a time when sort of computing started to be more personalized again for some people. I mean, I didn't use those kinds of computers for very much at all because they just weren't powerful enough to do the kind of scientific computation I wanted to do. I used some computers, actually even other kinds of computers at that time that were like the first portable computer, the Osborne 1, kind of the size of a small suitcase type thing, but in principle portable. I used that a little bit for word processing and so on. But really, I mostly used bigger time-shared computers. Then 1982, the time of workstation computers, the Sun workstation and related computers, it swung back to those being personal computers where you could have sort of all the computing you need on your desk, so to speak, or at least most of the computing you would need on your desk. And it's swung back and forth many times. It's swung between now, after a long time when it was kind of, you have the programs all running locally on your computer, then along comes cloud computing. And then let's be centralized again. And then along comes sort of blockchain. Let's decentralize in a different way for some kinds of things. Then along comes mobile computing. And it's again sort of a decentralization again. But then there's mobile computing communicating with the cloud, and it's centralized again. So I think this centralized, decentralized thing is sort of probably an accident of history, what came exactly when. For example, I remember this must have been 1982 or 83. There were sort of two competing technologies. One was the workstation on your desk, which actually did computation inside it. And the other was particularly a thing called the Blit terminal, which had been developed by someone I knew quite well at Bell Labs, which was a thing where it was just sort of a thin terminal, kind of like a Chromebook of today, where it was there was a nice bitmap display, but the actual computation was supposed to happen connected through phone lines, hence the sort of Bell Labs AT&T connection, connected through phone lines to a central computer. As it turned out, through details of sort of business situations, the technology of the workstation computer won out. It was partly a consequence, I think, of AT&T not being a company well set up to sort of go in a new entrepreneurial business direction, but Silicon Valley companies like Sun Microsystems being set up to kind of go and aggressively take that market, so to speak. So that's an example of something which I think at the time could have really flopped in the other direction. I mean, I know that, for example, when I was using computers in, what was it, 1978 through about 1982, my typical use case was to use a terminal that was just an alphanumeric terminal, so to speak, connected to a bigger computer. So if I'd had the ability to have a bitmap terminal with proper display, that would have just been, my workflow would have been the same, except then I could have done graphics on my display and so on. I mean, back in those days, I used to have a terminal at my office and I used to have a terminal at home. And I've been a very bad office worker, which is perhaps how I've come to be a remote CEO for the last 34 years or something. But I had a terminal at home, and I was always amazed coming from England, where the phone company was such that if you made a phone call, it cost you a certain amount per minute, wherever that phone call was to. In the US, local calls were free. And so I just hooked up an acoustic coupled modem, just took a phone with, one of those phones you actually hold up to your ear, like they always were at that time, a phone with a phone receiver, and put that in an acoustic coupler, which was a thing that would take the actual sound made by the sound made by the computer, transmit that in audio form over the phone line to a computer and so on. I just connected a phone to an acoustic coupler. I just left it connected for months at a time. I was very impressed that the technology of the phone system was such in California at that time that there just weren't any glitches. It glitched like once every 3 months or something. There would be a piece of noise on the line, but otherwise I could just leave my terminal connected to my remote computer all the time, and I would be able to just work that way. So it was really the fact that then by a year after that, I had a workstation computer where the whole computer was on my desk was sort of an accident of history. I think there are other things about kind of programming languages which have definitely been accidents of history. Sometimes things have been slightly better in terms of the way things work than others, and so things went in some direction. Sometimes it's purely because of some kind of perceived marketing thing, some hype or something, that things went in that direction. I mean, another big area where the things have worked in a funky way is with neural nets, which kind of was started off in 1943 and then sort of came to life in the late 1950s, disappeared again in the 60s, came to life a bit in the 1980s, disappeared again, came to life again in the 2010s. And certainly those flipping and floppings were more extreme than they needed to be. That was a consequence of various kinds of fads coming and going and so on. I think in terms of, well, let's see. I mean, there are certainly every kind of standard has lots of arbitrariness in it. Every kind of data transmission standard, every kind of way of representing things has arbitrariness. It's very much like the way human language has arbitrariness. I mean, the word for a cat didn't have to be cat. It could have been all kinds of different things, and it obviously is in other languages. It just needs to be something definite. And so it is often with standards for computer communication, communication of humans with computers, and so on. I mean, there are other things about computers and so on, which are surely accidents, things to do with the way the user interface works. Some things are sort of inexorable and kind of, oh, it was kind of obvious it would evolve that way. Some things were sort of the arbitrary choice at the time that just got sort of burnt in and everybody got used to it. I mean, certainly when it comes to sort of the details of things, the fact that a website specification starts, HTTP : / www, etc. That always struck me when the web was young. That always struck me as the most bizarre kind of druidic utterance that I think extremely few people understood. I have to say it really, really amused me in the beginning of the 90s when you started to see, trucks driving around proudly with URLs painted on them, so to speak, with all that HTTP, / www. And it's like, well, I think that was Tim Berners-Lee's invention, and it was a very arbitrary invention. And it's sort of very strange that it had that form. Now, at the time, the HTTP was competing with FTP, and the / was kind of a convenient way to represent the root of a sort of directory-like system, and the www was sort of an ad for the World Wide Web and all those kinds of things, and also kind of a convention for how websites would be set up. But those things are certainly quite arbitrary, and over the course of time, they have sort of decayed. You just see blah blah blah.com. Of course, .com is another accident of history. That was a consequence of the fact that the ARPANET was sort of built by the US as sort of the first piece of the internet that sort of went international. But at the beginning, it was like, at the beginning, there weren't any .coms, .mils, .edus or whatever. At the beginning, the first, when the internet was first up, when I first used it in the 70s, every host on the internet was specified by a number. So like the one that I commonly used at MIT was, I think, 235. And you would literally, to go connect to it, you would say at 235, and it would go to that host. I think there were 512 hosts in total on the internet, on the ARPANET at that time. Later on, there started to be email addresses. At the beginning, email addresses didn't have the form they have today of blah at blah. Instead, they were using UUCP, the Unix to Unix copy protocol, usually. That was a common way of doing them. And that was something where essentially one computer would call on the phone another computer, which would call on the phone another computer, and it would transfer your mail. And so a typical email address looked like blah, exclamation mark, blah, exclamation mark, whatever. And those successive exclamation marks defined where the computer should call next. In modern times, when you look at traceroute, for example, when you look at where does your data actually go to get to the domain you're trying to send it to, you'll see a series of hops like that. Back in the early days of email, those hops would be explicitly specified. Then along came things like BitNet. That was an IBM thing. I think there was a thing called NSFNet. It was a US National Science Foundation thing. These defined some slightly different conventions for email, and people would quote their UUCP address and their BitNet address and so on. And then that all got kind of standardized. When was that? That was, I think by 1986, it was not standardized, because I remember when I started my journal, Complex Systems, back in 1986, and we became the first journal to accept electronic submissions of papers. Kind of funny to think of that in these days, because even Nature magazine wrote an editorial about our journal as kind of the electronic publishing of the future, because we had things where you could send us your paper on BitNet, or you could send us a floppy disk of your paper and so on. I have to say it was a little bit embarrassing, but the instructions to contributors for the Complex Systems Journal, actually, I don't think got updated much in 25 years. And so 25 years later, we were still talking about, well, you could send it on a floppy disk if you want to. I think we finally took that out. But the evolution of kind of how it got to be, @ signs and so on for email, I think that was happening I think that had pretty firmly happened by certainly by 1990, but 1988, yeah, I was certainly using. I had a fixed email address from when we. I think we first registered our domain wolfram.com in 1986 or 87, and I was certainly using my email address from that time. Actually, we had first registered ri.com, wri.com. These days, it would be hard to register a three-letter name. But in any case, just to comment more on arbitrariness, for example, the things that are on the keyboard, the @ sign, the hash sign, the tilde, all those kinds of things, those are creatures of the ASCII keyboard. Those were things that were sort of standardized, I would say, by probably the mid-80s. The part of that was standardized earlier than that. I think the terminals that I used in the late 70s already had just those kinds of things on them. But at the time, there was still sort of a big sort of competition with this thing called EBCDIC, which was the standard that IBM had proposed and pushed for a way to specify characters. EBCDIC had a different set of special characters and a different encoding in terms of bits of characters. It eventually sort of went extinct and leaving over ASCII. That was important for me even when I was designing SMP, the sort of forerunner of Mathematica and Wolfram language that I built starting in 1979. I was able to use various kinds of characters like backticks and so on that I could standardly use, because I was pretty sure people would have ASCII terminals, ASCII keyboards. I seem to remember that we ported SMP to at least one machine that was an EBCDIC, and that caused all kinds of trouble for our specification of the language. So a few thoughts there. Let's see. Well, let's see. M. Rudo asks, was I involved in the building of OEIS? That's the Online Encyclopedia of Integer Sequences. The answer is no. That's a project that was started by Neil Sloan at Bell Labs back in the 1960s. I think originally he just had things on index cards, and eventually he published a book called The Handbook of Integer Sequences. Probably that was around 1970, maybe. I certainly had a copy of it very early on. And then, in a somewhat amusing situation, a chap called Simon Plouffe, who was a somewhat not particularly formally educated chap in Canada, ended up being very enamored of the online encyclopedia of integer sequences, and he typed it into a computer. It hadn't been in a computer before then. And then he collaborated with Neil Sloan to make I should say, yeah, to make, I think that was how the online version of the Encyclopedia of Integer Sequences began. Simon Plouffe was also notable for having invented this idea of being able to compute the nth digit of pi without computing previous digits of pi, at least in base 16, and with various footnotes to the fact that it works almost all the time, but you could imagine a situation where a sort of series of carry bits would build up where it wouldn't work. Simon Plouffe actually worked for our company for a little while at some point in the past. We've built things both based on OEIS, and we've also built a function called find sequence function, which is kind of a more algorithmic version of finding what sort of formulas for sequences might be. It's always a bit challenging for me. I find the number of times when I use OEIS and I don't just say to myself after I see a sequence matches, oh, I kind of knew that already, is rather small. And I think we've certainly put a bunch of sequences into OEIS. I think people have been putting the sequences that I've generated in there. I shouldn't start reading other questions while I'm still talking about a previous question. Let's see. Well, I'm going to jump around a bit. M asks, have you ever visited a place tied to a famous inventor or scientist that stuck with you? Oh, when I visited those places, they stick with me. I mean, I was amused to visit Charles Darwin's house, Down House in Kent, I think, in England, at some point, and to realize that Charles Darwin had a bunch of these sort of personal efficiency things set up for himself, like kind of the system of mirrors, so he could be sitting at his desk and see who was at the front door and so on. I found that sort of an amusing piece of personal efficiency that kind of reminds me of things that I've done. It was interesting to see Thomas Edison's lab in Menlo Park, New Jersey, mostly for kind of the idea that you have all these different capabilities that are sort of available nearby. I would say that the density of books was lower than it might have been. The density of contraptions was higher than it might have been. What other places have I seen? I mean, there are all kinds of other ones, which the Science Museum in London and maybe I think the Royal Institution in London, they have various kinds of, Humphrey Davy, Michael Faraday type kind of at least recreations of their sort of workspaces. I guess those are too sparse for me to find them all that exciting. I mean, when I visited, I like visiting labs. I find visiting labs very useful in terms of getting sort of a more intuitive understanding of what people are actually doing and the experiments they're doing. And an awful lot of the time, you go to a biology lab, for example, it's a bunch of transparent or translucent containers of liquid, and then things that look like kitchen appliances, so to speak. It's often very kind of similar and not very kind of sort of all of the high tech is in the level of molecules. You can't really see it on a large scale. I'm trying to think about other places I've been where where it was notable. I mean, I remember visiting Darcy Thompson's, the museum that had been sort of curated and then taken apart and then reassembled by Darcy Thompson in the early 1900s. Mostly interesting for sort of the strange critters that skeletons and things that are there. I remember at the Natural History Museum in England, there are sort of containers of critters preserved in formaldehyde or whatever, that this specimen collected by Charles Darwin type thing. That's sort of fun to see. Let's see. I see a question here from Jamie. When was the first museum started? I think the British Museum was the first serious modern museum. And that was late 1700s, I think. I think in antiquity, there had been things like zoos and the things like libraries, and people had collected things, but I don't know whether there was a public museum that existed at that time. I mean, I think the British Museum was sort of started at the sort of the height of pride of the British Empire. For better or worse, it accumulated many things from the British Empire. I think other museums, I mean, there was sort of a very big time, things like the London Natural History Museum was started in probably the mid-1800s. And sort of in time for the big enthusiasm about natural history and collecting kind of specimens from all over the world that was happening in the 1800s. I think then, more like in the very late 1800s, early 1900s, was sort of a big thing for anthropology, going to visit all the different societies around the world and sort of collecting things from there. That led to things like in Oxford, for example, there's a thing called the Pitt Rivers Museum, which is sort of charming because it's kind of a junk shop of the empire in some ways, or at least it was that way. Maybe it's changed over the years. I don't know. When I was a kid, it was that way. Because it was all this stuff that had been collected from, this random place somebody visited in the middle of Africa at some point in, 1920 or something, and somebody gave them this strange kind of, tiger sculpture or something, and it wasn't necessarily quite clear what it was, but it all sort of wound up in this museum. And I think the idea of a museum that is the notion of how things are presented in a museum has definitely changed over the years. I mean, I remember when I was a kid going to the London Science Museum, this is in the early 1960s, and most of what was there was objects of historical interest, like, the first big steam train, the first, some first optical device of a certain kind, all these kinds of things of sort of the artifacts. I mean, at the time it was called, I think, the Museum of Science and Industry, and it was kind of the achievements in science and industry as historical artifacts. Back at the beginning of the 60s was a time, I remember the London Science Museum in its basement opened this shockingly new hands-on exhibit space where kids and others could actually poke at exhibits and not just look at them behind glass in glass cases. And that was a thing that started at that time. I think it also had started with the Exploratorium in San Francisco, started by Frank Oppenheimer, Robert Oppenheimer's brother. That was this notion of sort of the hands-on museum was something that really advanced, starting, I think, in the early 1960s. Before that time, people would be like, that would be shocking to imagine the kids actually touching a thing. Rather, keep those valuable historical artifacts behind glass for people to look at, kind of seen but not touched type thing. I think in more modern times, there's sort of been a whole discipline of museum design. There's some very well-designed museums that have kind of a more sort of a tell the story type approach, rather than what was the case in the past of just here are things and each thing has a caption kind of thing. Let's see. Oh gosh, so many interesting questions here. Well, let's see here. Okay, very different kind of question. M. Rudo asks, what is the history of virtual particles? Okay, so I should explain what virtual particles are. In physics, starting in the late 1800s, it was discovered that matter is made of particles. That wasn't clear until the late 1800s. But in the 1890s, the electron was discovered by J.J. Thomson. And then later on, by 1905, Einstein had sort of suggested the idea of a photon. And then not long after, the atomic nucleus was discovered, and the idea of protons were discovered. Somewhat later, I think perhaps it was even the 1930s, that neutrons were sort of separately discovered as explicit particles. And then later on, a whole zoo of other particles starting in the 1930s with the muon and the pion and all kinds of other things. But the idea that there are discrete elements of matter, the electron, the photon being two key examples, proton being another example, that was a thing that sort of was known at the time when the sort of formal mathematical development of quantum mechanics started in the 1920s. So by 1925, there were sort of ideas about wave functions, about this sort of notion of amplitudes for particles to be somewhere or another, and that was sort of embodied in the Schrodinger equation, and so on. And then one of the big questions was, okay, we've got a thing that represents one electron that could be here or there, like one electron in a hydrogen atom or something, could be here or there. But what happens when you have a variable number of particles in a field, like an electromagnetic field? There isn't just one photon, there's a variable number of photons. And so that led to the idea of a quantum field, the idea that you would have not just a description of a single photon or two photons or three photons, but something where it's a so-called Fock space of many possibilities of any number of photons. And so that was a thing, the mathematical development of which was very difficult and still continues to this day. But by the end of the 1920s, people were sort of talking seriously about quantum fields, things where there will be variable numbers of particles that existed. Well, that led to the idea that particles could be emitted and absorbed, and sort of the notion of that happening. Well, the question is a photon that's emitted and then very soon thereafter absorbed, is that a different kind of thing than a photon that just travels through the universe as a piece of light sort of forever, so to speak? Well, what was realized when quantum field theory started being developed, this is 1930s and beginning of the 1940s, the idea of working out sort of the mathematical structure of kind of quantum fields. And at first it was just like, well, you've got this blob of particle-like stuff that is a field. How are you going to deal with that? The S matrix invented by Heisenberg was sort of a big piece of that story, because Heisenberg basically just said, well, don't worry about what's happening inside. Just say, what are the initial particles that come into an interaction? What are the final particles that go out of an interaction? Let's now just try and figure out a scattering matrix that represents the transformation from the initial set of particles to the final set of particles. Then the thing was on, well, how do we work out S matrix? How do we work out what that transformation from initial states to final states is like? And that led to the idea of the perturbation expansion, where you assume, well, the particles don't interact very much. We can just have a coupling constant, something, for example, the most famous one is for electromagnetism, the fine structure constant alpha, which is about 1/137. And you just say, let's just consider the case where they interacted once. and contribute to the S matrix, interact twice and contribute, interact 3 times, and so on. Well, that led to a bunch of formalisms for thinking about sort of how to deal with those interactions. The most famous of those is Feynman diagrams, invented by my friend Dick Feynman in the 1940s. And Feynman diagrams are sort of this way of showing how a particle, like an electron, can sort of come in, then it could be, for example, interact with a photon, and then produce another photon or whatever. It's kind of it was viewed as sort of a space-time picture of how particles interact, rather than the kind of pure mathematical blobble of stuff that had come out of sort of the pure formalism of quantum field theory. There's kind of a competing formalism called source theory due to Julian Schwinger that was much harder to understand for people. Feynman diagrams had this kind of intuitive appeal of you've just got a picture of where the particles go. Well, was it really where the particles go, or is it some representation instead, as I now view it much more, of sort of the causal relationships between this interaction that happened between these particles, then this same particle, that same electron, ended up in some other interaction, and so on. It's a representation of those things. But as soon as you have Feynman diagrams, you have this kind of notion of virtual particles, particles that don't survive long. They're emitted and they're absorbed a very short time later. And that's that's something where the way the formalism works out, those particles can have characteristics that are not the same as the characteristics free versions of those particles have. In particular, and it's sort of a consequence of the uncertainty principle, those particles can have effective masses that are very different from their ordinary free masses. So photons, for example, which are normally massless, a virtual photon can have kind of a high mass. And in fact, what you do when you work out a Feynman diagram is you work out you integrate over all possible masses of those virtual photons. Now, there have been a couple of other things that had happened that have sort of played into the virtual particle story. One was Hideki Yukawa's work, and another was Paul Dirac's work. So let's see, the Yukawa story is maybe a little easier to explain, and that had to do with the, well, there was a question of what held nuclei together. Electromagnetism has the feature that like charges repel. So 2 electrons will repel each other. An electron and a proton that have opposite charges, they'll attract each other and can make a happy hydrogen atom together. But the big mystery was in a nucleus where there are a whole bunch of protons jammed in, like in uranium, there are 92 protons jammed in together with a bunch of neutrons. How could it be the case that the nucleus didn't fly apart because of the electrical repulsion of all those protons? Well, a chap called Hideki Yukawa in Japan in the 1930s suggested the idea that perhaps there could be a thing that was a bit like electromagnetism, but not really electromagnetism, that was not like photons being exchanged, which was the sort of photons are the carriers of electromagnetism, but another kind of thing, another kind of particle. Later, they were called pions. But the idea was that those would be particles that have a mass, even when they're free particles, they have a mass. The fact that they have a mass means that the range of the interaction would be limited, whereas with a photon, which is massless, you have this whole inverse square law story. With a massive particle, you have an exponential fall off in the strength of the interaction. So Yukawa suggested that this might be what held nuclei together. And sure enough, a few years later, a particle a bit like that was discovered in cosmic rays. Actually, it wasn't the pion at first. At first, it was the muon, which has a mass of 105 MeV, million electron volts. The electron has a mass of 0.51 MeV. And so people thought, oh, the muon is roughly the right mass to be a pion, because people knew the rough mass of the pion from the size of nuclei and so on. But actually, it wasn't the pion. The pion was discovered a few years later as a mass of 135 MeV. And it was the muon is a different and still mysterious kind of thing that's just like a sort of heavy version of the electron, and nobody really knows quite why it exists. Well, but virtual particles in sort of the Yukawa story sort of demands virtual particles but the formalism of quantum field theory wasn't as well applied to strong interactions because of this idea of a perturbation expansion where you could say one interaction, two interactions, three interactions doesn't work so well when the strength of the interaction is about one and where everything involves a huge number of interactions. That was sort of one of the sort of difficulties of particle physics and quantum field theory up until the 1970s, was understanding how could you compute things in the strong interactions that held nuclei together. We still have trouble computing lots of things there, but what was discovered in 1973 was this phenomenon of asymptotic freedom in QCD, which was the sort of theory of what was inside the protons and so on, quarks and gluons. It was a theory of those things, and what was discovered was that if you sort of bash the quark hard enough, its effective coupling will be much lower. And so you can do this kind of perturbation expansion. In fact, some of my early efforts in particle physics involved doing a bunch of calculations of that perturbation expansion for QCD to work out the rates of various kinds of processes where conveniently, because it was a very new kind of thing, nobody had worked those things out yet. So I had kind of the fun of doing that. But in any case, another part of the sort of related to the virtual particle story was Paul Dirac's work in the early 1920s on the Dirac equation. So no, it must have been later 1920s. So Erwin Schrödinger had come up with his Schrödinger equation, which was an equation that described non-relativistic, things moving much slower than the speed of light, particles in quantum mechanics, and described sort of this quantum amplitude, which was later sort of understood as being related to the probability of how likely it is to find the particle in a particular place. He had created the Schrödinger equation, which was an equation for this non-relativistic kind of wave function, particle amplitude wave function thing. So the question was, what would happen if things were not non-relativistic? If you could deal with particles that were traveling close to the speed of light, how then would that work? Well, Dirac came up with a theory for that, for electrons in particular, the so-called Dirac equation. And one of the things that happens in the Dirac equation is that it's if you start saying, well, what are the energy levels for an electron in the Dirac equation? What possible energies can an electron have? Turns out it has lots of possible positive values, but also it has lots of negative values as well. So how did Dirac interpret that? What he interpreted that as is, well, there are all these possible negative energy levels for an electron, but let's imagine that all of those are filled up with sort of the electron field or the negative electron field throughout the universe. And the only thing you get to notice is a hole in the negative electron field, which shows up as a positively charged particle. And that was the idea of antiparticles. We now wouldn't really so much talk about this Dirac sea, as it was called, of negative energy particles. We'd rather just sort of say, well, there are particles and there are antiparticles, and we're not going to discuss sort of whether there are what there is in the way of sort of a background of these things. Now, a thing that happened as a result of quantum field theory is that this idea of virtual particles, the particles can come into existence for a short time, then disappear again. That idea happens not only when there's an interaction going on and sort of you're kicking things and you're putting energy in and so on, but it also happens in the vacuum. The quantum field theory vacuum is a very complicated thing because it contains little fluctuations of all these different possible virtual particles. And that's something that became somewhat understood, I would say, certainly by the 1940s. And it was very confusing to people. It's like, well, the vacuum is full of an infinite number of these kinds of vacuum fluctuations. That was sort of related to the Dirac sea story for the Dirac equation, but it isn't quite the same idea. The question of what that means for the vacuum, that it has full of all these fluctuations, is a complicated one. For example, I think it was the late 1940s, Hendrik Casimir in the Netherlands came up with this idea of the Casimir force, which is something where when you have just two metal plates in the vacuum, nothing's going on. There's a small force of attraction between those plates. That's a consequence of the fact that the vacuum fluctuations between the plates are a little different than the vacuum fluctuations outside the plates. And that was something that was sort of just being understood by the late 1940s that things like that worked that way. There were lots of confusions in quantum field theory. There's a sort of whole story of what's called normal ordering, which is kind of a kludge to deal with the fact that you should get sort of submerged in vacuum fluctuations. Then that same issue came up again when people started thinking about sort of how do you merge gravity with quantum mechanics? Because one of the issues is when you have all these vacuum fluctuations, they are associated with huge energy density in the vacuum. But the problem is, if there's all that energy density in the vacuum, why doesn't it have a gravitational effect? Why hasn't it curled the universe up into a tiny ball? Because there's so much mass, effectively, purely in the vacuum. And that remains a mystery. I think in our models of physics, that finally gets resolved, because in our models of physics, we have a situation where the structure of space is actually made from processes that can be interpreted as those kind of virtual particle-like processes. And so it isn't the case that the virtual particles on one side are weighing space down and then it's having an effect on gravity. Rather, the structure of space itself is made from those processes that one can also interpret as virtual particles. So that's a little bit of the story of that. I mean, a virtual particle, it's more getting into the physics of it, but it's something where it's really an inner part of the computation of what the probability for some scattering process will be. Oh, there's some virtual particle that's exchanged, and that contributes to the mathematics of working out the scattering process. And the big sort of complexity of Feynman diagrams and working out things in quantum field theory is you have these loops where you have virtual particles that can exist kind of in these loops. And when you work things out, you do this integral over sort of all the possible masses and momenta of the particles in that loop. And those integrals get very complicated, very hairy, very needing of computer algebra and so on to be able to be done. I mean, in our physics project, we're starting to understand more about what those loops in Feynman diagrams really mean. And it's an interesting story, not yet fully told. And it's a complicated story that has to do with kind of this, probably has to do with the thing that I'm preliminarily calling subtime, which is kind of a version of things happening that will not be perceived as the passage of time by an observer. I should mention that in the sort of story of electrons and positrons, their antiparticles, and Feynman diagrams and so on, one piece of that story was Dick Feynman and his thesis advisor, John Wheeler, talking about sort of how could one understand things in physics, and how could one sort of set up this representation of what was happening in particle interactions and so on. One of the mysteries that they talked about a bunch, apparently, I remember Dick Feynman telling me about this, was the question of why all electrons are the same. It seems very surprising that why, they all have the exact same mass, the exact same charge and so on, even though they might have different momentum in different situations. So the idea they had, well, maybe there's just one electron in the whole universe, and it's going forwards in time, and it makes an electron there. It's going backwards in time. It's representing a positron there and so on. And there's just this one electron. And every electron we see is just an instance of this one electron. Well, that theory doesn't actually work out, but that was part of the kind of impetus to invent Feynman diagrams and this kind of space-time representation of particle interactions. I would say in modern times, I have a different view of why are all electrons the same. And it's an interesting story because I kind of have the suspicion that all electrons look the same to the outside, but aren't actually the same on the inside. It's a very similar story to the story of black holes, where all black holes with certain mass and sort of spin look the same on the outside, even though they might have completely different, crushed civilizations on the inside. Let's see. There's a question here from Brady. What do you think Roman dodecahedrons were for? They're these fun museum exhibits. There's one, I think in the British Museum that I've seen. They're dodecahedra, and they have these little sort of blobs on each corner, and then they have cutouts on every face. What were they for? Well, maybe they were like jacks that were used in a game. Maybe they were things where you would kind of wind thread around them. I kind of wonder, I don't know whether anybody's looked at kind of an almost molecular level of whether there's anything kind of left over in the dodecahedra that are now found. I mean, this is always a very interesting question. When you have an artifact from some time in history where we don't have sort of a common thread of explanation of what it was, what did that artifact do? And we have many examples where we just don't know. From Stonehenge on, it's like we can guess by certain sort of features of the object itself. We have a good leg up if we had some description from some writer who might have said, oh, they went to Stonehenge and did all these weird rituals or something. But we don't have that. We just have the stones. And sometimes in more modern times, there's sort of molecular scale archaeology that can be done where it's like, well, actually, this stone has, the remnants of sheep blood, and we can even work out the DNA and discover that sheep came from hundreds of miles away or something. But that's kind of a new perspective, a new way of looking at sort of what did artifacts do. But otherwise, one's kind of stuck with kind of, was there a contemporary description that kind of carries through today? Do we even understand that description? Or is there a thing today that we can look at and say, oh, that looks just like what existed at that time? I mean, if we see something like a knife, we kind of knives exist still today, and we can kind of guess that's what that was for. I think, forks, for example, were a much more modern construction. And so we wouldn't, if we saw whatever the Roman analog, the Etruscan analog or something of a fork that doesn't have at all the shape of a fork, I'm not necessarily sure how much we would recognize it. And I think so it's always a challenge to understand what these things were for. It's even a challenge to understand when people write about things and they say the name of some animal, but that's not what we call the animal today. And it might be obvious that everybody had seen one of these animals, and so they didn't describe it very much. They just sort of said, and the such and such bird was flapping around or whatever. Well, then there's an interesting problem of, can you get enough clues from the ancient literature to match up what is the modern critter with what was the ancient critter? Actually, Darcy Thompson, who I mentioned earlier, is somebody who wrote a book called Greek Fishes, another book called Greek Birds. And the goal was specifically this, to match up kind of the modern species with its modern name with the ancient species and its ancient name. Let's see. Double comments, shortly after he proposed general relativity, it says, Einstein had a hypothesis that matter is composed of curved spacetime. Have I heard of that? Why didn't that work out at the time? Yes, I have heard of that. So Einstein kind of imagined that perhaps everything in the universe is just space. He didn't get very far with that idea. He didn't understand the idea of black holes. That wasn't really understood until the 1960s. It was somewhat understood by Oppenheimer and so on in the 1940s, but it wasn't really understood what black holes were, and the notion of singularities and the possibility that there would actually be a physical instance of a black hole. Even in the late 70s, it was still very unclear. I mean, there was a particular thing, Cygnus X1, that was an X-ray emitting star that was thought maybe it was a black hole with matter accreting into the black hole and emitting X-rays as it got really fast, as it got pulled into the black hole. But it wasn't, the true existence of black holes wasn't clear for a long time. So the notion that you could have something that's sort of purely a bundle of gravity, so to speak, that has an existence was something that wasn't really known in Einstein's time. Now, Einstein also tried to think about how he tried to make a unified field theory where, among other things, electromagnetism and gravity were sort of all combined together. There were these things called Kaluza-Klein theories that originated, I think, in the 20s, where the idea was that electromagnetism was like an extra dimension of space-time, was the dimension that represented the sort of gauge degree of freedom, so-called, of electromagnetism. Those theories got repurposed when string theories came out and people started talking about extra-dimensional space and the possibility that there would be a sort of extra dimensions that were curled up very small. That was sort of a rerunning of the Kaluza-Klein theory idea from much, much earlier. But that was something that was being talked about and Einstein had thought about. Then there were some things called geons, and the aforementioned John Wheeler was involved with those. That was kind of intended to be this bundle of electromagnetism and gravity that was sort of a self-contained thing. It didn't work out because geons were found to be unstable. And, it could have been the case that you have a bundle of electromagnetism and it creates energy and mass, and that mass then creates gravity, and that sort of all holds itself together with sort of pure energy, in a sense, pure fields, pure, no real matter, no obvious sort of protons and nuclei and things like that in the picture. It didn't work out. I mean, later on, for example, string theory is an attempt to make a theory where sort of really all there is association of those strings that correspond to different kinds of particles and so on. So it's kind of going a little bit in that direction. It also hasn't worked out terribly well. In our models, we're sort of going completely in that direction. There's nothing in the universe in our models other than space. But very differently from these previous models, space has a structure. Space is this giant hypergraph, and the features of that hypergraph are what correspond to the existence of particles and things like this. So it's an interesting story. Now Wheeler in the 1960s had this idea of what he called geometrodynamics, which was some kind of idea of, I think, partly maybe discrete in some ways, I'm not sure, theory of the structure of space-time. He wrote a book about it. It would be a great book, but for one horrible glitch, which was that in that book, he believes that neutrinos are gravitons. Neutrinos are the carriers of the gravitational force, which is completely wrong. And so that book has sort of seems to have vanished without trace. I got a copy of it a couple of years ago. It was somewhat hard to track down. And then I realized, it's an interesting book. It talks about kind of the structure of space-time, how to think about discrete space-time and so on. But then it has this kind of horrible boo-boo of neutrinos or gravitons, which most of the argument of the book doesn't really deal with. But I think that's sort of why that effort was buried. And I think then this idea, the geometrodynamics idea, shows up again in the book that John Wheeler wrote with Charles Misner and Kip Thorne when was that? Around 1970, early 70s. There's a chapter, a lovely chapter at the end of that book that talks about kind of the way you might construct sort of space-time from something lower level, and has this kind of analogy of chainmail, of sort of how you make space-time out of sort of knitting together kind of pieces of chainmail that you could knit together in potential, I don't think they say this, but they could have said this, in different numbers of dimensions and so on. I never really interacted much with John Wheeler, unfortunately. John Wheeler was kind of an enthusiast of things like discrete space-time. He had this kind of notion of it from bit. He was very big on these kind of quick aphoristic versions of how science might work. I exchanged letters with John Wheeler a number of times, not particularly usefully. I mean, it was mostly, I would say, him saying to me, "Oh, you should study things, and that will be, it's worth studying all this fundamental physics stuff and so on. And then, and I think not really engaging on the things that I'm not sure. I certainly exchanged letters with him about things like cellular automata, but I don't really remember what was in those letters. I met him only when he was 95 years old and in not particularly good health. And it was kind of a bit of an unfortunate meeting in many ways, because he really was not I don't think was fully with it. But we were talking about the NKS book, my new kind of science book. This must have been in the 2003, 2004 type time frame. And the most notable part of that meeting, which was a sad thing to report, but it's an interesting piece of history, was he's looking through the new kind of science book, and he looks up and he says to me, you know who you should talk to about all of this stuff? There's this chap over at the Institute for Advanced Study. I was meeting John Wheeler in his office in Princeton University. There's this chap over at the Institute. His name is John von Neumann, and he kind of spells out the name. And I'm like, unfortunately, John von Neumann died before I was born. And, I think this is something, I notice it even in my advanced but not so advanced age, that it's often hard to remember the sequence of things. It's like who was alive at the same time as who type thing, or who worked at our company at the same time as who. You can be wrong by a decade or two. And well, given that our company is 4 decades old, that's possible there as well. And it's for me at least sometimes hard to remember, oh, did this overlap with that, or was it off by a decade? So I don't fault John Wheeler for being off by a full 50 years or so in John von Neumann being a chap who was just down the road type thing. Let's see. So that's, I think, I should mention in the story of sort of matter as composed of curved spacetime, I'm pretty sure that David Finkelstein worked on that a bit. David Finkelstein, I knew somewhat. He was a very original thinker working on sort of the intersection of gravitation theory and quantum mechanics and so on, invented things like coordinate system for studying black holes, and invented kind of ways to think about quantum mechanics and kind of quantum logic and so on. It was a sort of a forerunner of quantum computing. David Finkelstein had the unfortunate feature that he finally admitted to me at some point, that he wrote many papers and they were difficult to understand, but you would think that in aggregate they would be easier to understand, but they were not. And as he finally told me, because I've been so confused by this, he says, well, I wrote these things and sometimes I figured out the thing I'd written before wasn't quite right. And so I wrote something new, but I never really bothered to explain that the thing before wasn't right. So you see this whole sequence of things, each one interesting, and they just don't fit together, because they really don't fit together, because they were reworkings of things sort of going back on previous ideas and so on. But he was, I think, involved in this whole story of thinking about sort of, could one use sort of pure gravity as the source of gravity and so on. I think he was involved in that. There were this idea of sort of the unified field theory was one that Einstein that was a brand that Einstein talked about a bunch towards the end of his life. He died in 1954, I think, 55 maybe. He was sufficiently much of a media figure in the US that people would report on, Professor Einstein's unified field theory has advanced in this way or that way. Most practicing physicists at that point had sort of said, oh, Einstein is irrelevant. He didn't really jump on the big quantum mechanics bandwagon that started in the 1920s and 1930s. He's off going in a different direction. I'm not sure his direction was actually quite so bad, but in any case, it was something people didn't follow that closely. Actually, Werner Heisenberg who'd come from the quantum mechanics direction, himself went into kind of the unified field theory idea. People also didn't pay much attention to him. I will say, faulting myself for something in 1976, when I was a kid, somebody said to me, "Oh, you should go to this lecture that Werner Heisenberg is giving in Cambridge." And it would have been easy for me to do that. And he said, "Oh, he always likes meeting these young whippersnappers type thing." And I was like, I don't care. He's been working on stuff that seems like sort of a bad idea for years on this unified field theory. I'm just not really that interested. I'm more interested in the future, so to speak. Big mistake, big shame. It would have been very interesting to talk to Heisenberg about what he thought about unified field theory, because as I learned many years later, he had a sort of a theory of kind of using sort of nonlinear equations and things as a way to understand what particles might exist. I kind of think, although some historian of science told me I'm probably not right about this, that Heisenberg's early work in fluid dynamics might have informed some of what he did in this kind of unified field theory, where he was thinking about sort of this field that represents all particles being a little bit like the field of velocities in a fluid that can have all kinds of complicated features and so on. Let's see. Okay, maybe my last question for today from Hill. Do you think there are any other scientific figures who could carry a blockbuster movie like Oppenheimer? I have to say I was not a fan of kind of the scientific aspects in many ways of that movie. I mean, that movie felt to me like it was more like kind of a soap opera level description of people being petty with each other, with an atomic bomb blowing up in the background, so to speak. I think so, a well-made movie that wasn't really a movie so much about a scientist. There are other movies. I'm afraid that it is often the case that the sort of historical accuracy of movies is about scientists in particular is sort of inversely proportional to their quality as movies. And I think that might just be coincidence, or it might be something that's inevitable. I mean, there were a couple of movies that came out, one that I was slightly involved with about Ramanujan, that was a really quite accurate movie. And at the same time, a movie came out about Alan Turing that was sort of wildly historically inaccurate, but in many ways was a stronger movie as a movie, gave people completely the wrong idea about the personality of Turing and many other things. But I think sort of the story of Ramanujan is an interesting arc of a story that was told pretty well in the movie. And, it had to do with, well, he grew up in India and he was sort of in a not completely sort of down and out setting, but he wound up as a clerk at the port of Madras, doing all kinds of mathematical calculations. Probably he did his actual job in 10 minutes a day because he was a very, very fast calculator. But then he spent the rest of his time doing sort of experimental mathematics. Then he writes this letter to G.H. Hardy, who realizes that, yes, there's something interesting here, and gets Ramanujan to come to Cambridge, which doesn't work out so well. And Ramanujan dies a few years later. It's kind of an interesting arc of a story. I'm not sure it quite has I mean, in a sense, the punchline, which I don't think was as well told in that movie as it could have been, is, the way we compute pi today comes from Ramanujan, or at least one of the ways. The way we do all kinds of things that are relevant for computer networks comes from Ramanujan. There are lots of things that come from Ramanujan, and that's kind of the heroic end of that story, rather than the poor chap died of tuberculosis being brought to the British climate, after a small number of years type thing. But I think, there are other movies one could certainly imagine, the Ada Lovelace, Charles Babbage story. The problem is it sort of has a great ending. The great ending is the modern computer age, but in its time, it doesn't have such a great ending. I mean, Ada dies of cancer at a young age. Charles Babbage lives many more years and doesn't really, and writes a lot of polemical books and doesn't really work on the stuff that he was on his computation ideas. So in that sense, it doesn't have a sort of a great arc of a story. I think there's a movie about Dick Feynman, which I have to say, I realize I have never watched, even though I got the DVD for it years and years ago, and I've never quite reached the threshold of watching it. But I think it more has to do with sort of the personal story of his first wife, who was kind of dying, actually, also of tuberculosis, at a sanatorium near Los Alamos, near the Manhattan Project. And I think it mostly has to do with that personal story rather than sort of a story about science. I mean, at some level, the sort of arc of lives, and a lot of movies are at some level mostly stories, mostly about people, and I think the story of what the science is a different kind of thing. I mean, there are other movies like the movie about John Nash, Beautiful Mind, that was both a good movie and a sort of a good story. I mean, that one, the arc of that story managed to get told in a way that seemed to be pretty compelling. But it was much more of a human story about psychiatric issues and so on than it was a story about the mathematics. I think I realize I don't think there's ever been an Isaac Newton movie. I don't know what it would be like. I mean, it could certainly tell the story of Isaac Newton and his adventures as controller of the mint and losing much money on the South Sea bubble, all those kinds of things. But I'm not sure. I mean, I suppose from a human point of view, there's kind of there are triumphs to be told there. Yeah, I really don't think there's ever been a movie about Isaac Newton. That seems like one that would be almost an obvious one. I think I can imagine some scurrilous movie about kind of the priority disputes between Newton and Hooke and Newton and Leibniz and so on. I don't know whether that would make an interesting movie. It's certainly something that there's lots of human intrigue and so on and story there. That's one that I can think of. I mean, I suppose in terms of other scientists, there's a lot of interesting personal stories. Sometimes the science is not as dramatic as it might be, but the story is pretty interesting. Sometimes the science is dramatic, but the story is not terribly interesting. The story is a very simple life at some level. All the excitement is in the science. So I think, but it's an interesting question. I think I'm trying to remember what other. I've been sort of peripherally involved in various sort of attempts to come up with ideas for science-themed movies, and there have been various other kinds of people who've been talked about. But I think I'm realizing I don't think there's even an Einstein movie, even though Einstein was such a famous character in sort of the public perception of science in the mid 20th century. I mean, I have to believe that there's some kind of sort of story of the emergence of the 1905, miraculous year that Einstein had, and so on. And there's probably some arc of a story around that. I'm realizing that's surprising. Nobody has made that movie, so far as I know. And I think there have been sort of documentaries, but not a kind of fictionalized sort of first-person movie, so to speak. It's. I mean, yeah, I have to believe there's quite a bit there. I mean, going into the letter to what was it? I guess it was to Truman about the possibility of an atomic bomb and so on, and sort of all the adventures about Einstein's involvement with the founding of the State of Israel and so on. There's certainly a bunch of more human story, even though I think Einstein, as a day-to-day person, would probably have said of himself, and it probably would be true from the outside, that he led a fairly simple life. I mean, and didn't, other than, as he said, I think when somebody asked him when he moved to the Institute for Advanced Study in Princeton in the 1930s, somebody said, what scientific equipment do you think you will need at the Institute? And he replied, I think this is a true story. I've certainly heard it. I think, yeah, I don't think this is an apocryphal story. He replied, well, the main thing I need is a garbage can to throw away all of the bad ideas that I have over the course of time. Well, I should probably wrap up here and leave it at that. I see a bunch of other interesting questions that I will be happy to try to address another time. But thanks for joining me. I will say that one of the things I'm planning to do is people have asked a bunch of times about sort of stories from my life, and I've been telling a lot of things that are sort of third-party science stories and so on. I thought I would try and do some live streams about sort of stories of my life and trying to tell them. We may be starting that in a couple of weeks, and hopefully we'll announce that. Anyway, thanks for joining me today. Bye for now.